So I've been asked to explain reduction to linear form again. So I will do. Now I'm going to do it with this example here. It says convert y equals 99 times 0.5 to the power x to linear form. Right, if you were to plot the graph of y equals 99 times 0.5 to the power x, you get the graph on the right here. Okay, and you can see that it's an exponential graph, obviously, and it's quite hard to read off values. It's very hard, actually, in fact, probably impossible to read off values when x starts to get a bit bigger. Okay, and we also, if we were to go up on that graph as well, it'd be hard to find the y-intercept and stuff like that. So, and remember I gave the example of this happened during COVID, but obviously the graph went the other way. And what they can do is to convert it to linear form, what you basically have to do is take logs. Right, so we're going to take logs. I'll show you what to do. I'm going to take logs of each side. Now here we've got a times sign, so just be careful of that. If it was an add, you'd have to do something different in a minute. But for now, I'm just going to take the log of both sides. Okay? And then we're going to, because we are multiplying here, we know from our log laws that that is the same as log to the base y equals log 99 plus the log of 0.5 to the x. Okay, happy with that? When you multiply inside here, you can split that up into a plus there, because when you merge those two logs, you'd multiply them. Okay, and then I'm going to bring that power of x forward, because I don't like it being over there. Whoop! Right, okay. And this gives you the log of y equals log 99 plus x times the log of 0.5. Right, now I'm going to write this in the form log y. I'm just going to move these round so I've got my x bit at the front. You don't have to do this, but you'll see why I'm doing it in a minute. Okay, so all I've done is wiggle around the order there. I've not changed anything. Right, now if we compare this to our equation of a straight line, y equals mx plus c, you can see what I'm doing here, then you can see that our plus c bit is the log of 99. Our x, well that's x there, so our m is log 0.5, okay, and our y equates over here to this log y here. So our log y, whee, okay, right. So if we were now to plot this, we will be plotting the log of y against x. So on our y-axis, instead of having y, we'd have log of y, or natural log y, any base you like. Now our x is still just x, it's not log x, it's just x. See, these are still the same. Our gradient of our linear line, m, will be log of 0.5. And our plus c, our y-intercept, would be log 99. Okay, so what we actually want to do now is to plot the log of y instead of y on our y-axis against x here. Now you'll have seen different ones where when you do your logs, you do get a log of x, but on this one we don't get log of x, we just get x on its own. If we did get a log of x, then you would plot the log of x on your x-axis. Okay, so what I'm going to do now is go back to GeoGebra and plot this. So we've got the log of y equals x times, hang on, here we go. So log of y equals x times the log of, is it 5? I have to go back again now, sorry, of 0.5. Plus the log of 99. Okay. Now hopefully you can see that there now. We have now got a straight line. Okay, we've got log y equals, you can't see that because the screen's not quite in the right place. There we go. I've plotted log y as our function of x is equal to x times log to the base, it's taken log to the base 10. Doesn't matter what log base you take. But you can see now that we've got a straight line. Now our y-intercept, if we zoom in here, is around about 6.7. And that's when x is 0. Sorry, our y-intercept is 2. And our gradient, well, I'm not entirely sure what it is, but it looks negative. Okay, now we could work that out. Or we could work it out by choosing 2 points on that line. Whoops, hang on. 2 points on that line and working out the gradient between the two of them. Or we can go back to our equation and work that out. Okay, so we can say that our y-intercept, let's go back over here, so around to our linear graph. Our y-intercept is 2. So we can say 2 is equal to log 99. Is that true? Hang on a minute. Log 99 equals... Oh, it is. It's 2. Who knew? So our y-intercept is log 99. So in case they ask. So our y-intercept, which is approximately equal to 2. And our gradient of our line is log of 0.5. Okay, now that was us doing this from scratch. But sometimes they give you the graph and ask you to work backwards from it. So I'm going to go and find one of those and then I'll do that. One moment. Hello, right, I'm back. I've got one. So this is an AQA exam question. So the number of branches of a high street store decreases over time. This trend, which is of the form y equals ab to the power x. So they're telling you what form it's taken. Okay, it can be monitored over a number of years, and they want you to find a and b. Okay, so we want to find a and b. Right, so the way to do this is to reduce it to linear form. So the first thing you're going to do is take logs of both sides. So you're given the equation y equals ab to the power x. Okay, so we're going to find log of y is equal to the log of a b to the power x. Okay, I'm going to split that up just like I did before into the log of a plus the log of b to the power x. And this is very similar to the one that we've just done. We're not going to need to take the log of x because we're just going back here like so. Right. So we've got the log of y equals the log of a plus x times the log of b. So this tells us what we're going to plot this time is the log of y, and that is equal to x times the log of b. So on our axes this time, we're going to have the log of y, like we did last time, on our y-axis, and x on our other axis. Now, if you're going to plot that, which is what this question is asking you to do, then you need to calculate the log of y. So you're going to need another row in your table, and you're going to need to work out the log of y. Okay, so I'll tootle off and do that now. One moment. Hello, right, I'm back. So I tootled off to Desmos and I plotted my log of y here, this log here, against our x values here, and we get this beautiful straight line here. Okay, so I'm going to take my straight line, which is log y on one axis and x on the other. Okay, and we can quite clearly see now what's going on from this. So, okay, let's just get it in the right place. So, there we are, right. Whoop. Okay, so our y-intercept, which we can see from here, is 2 point something. So if we look at our y-intercept, there is about 2.85 maybe. So let's say our y-intercept is 2.85. Now, if we compare that to our equation here, our y-intercept is this log a bit, isn't it? Okay, because log b is our gradient, because if we had it in the form y equals mx plus c, this bit would be the plus c bit. Okay, so we need to do a swirly-whirly log to unknit this. So this is an invisible log to the base 10 here. So swirly-whirly log, we've got 10 to the power of 2.85 will give us our a. So 10 to the power 2.85 equals 707.95. So let's go for 708. So a is 708. Our gradient, which is our log b. Okay, so how are we going to calculate our gradient? Well, we can take any 2 points on the line. They're all on an exactly straight line, so we could take any 2 points we like. This one looks like an easy one. No, does it? Oh yeah, that one and that one. Oh, that's a lovely straight line, isn't it? Okay, so this is going from 0 to 5, so that's 5. And this is going from 2 up to about 2.85, so that's about 0.85-ish. So our gradient is changing y over changing x. And again, we're going to do the same thing. So now this all depends on how accurate your approximation of that y-intercept is. If you're going to do this properly, you could use 2 actual points, but you know, and actually use the log values or whatever. But I'm just approximating this here, and it will say approximate anyway. So log b is that, so 10 to the power minus 0.17 equals our b. So 10 to the power of that is equal to 0. I'm using my son's calculator here. It's a GCSE one and it's about 80 years old. B is equal to 0.67. Let's round that up to 0.68. To 2 decimal places. So we've found our values of a and b then, which is all this question asked us to do. Use the data from the monitoring to find a and b. So we've found a is approximately 708. Let's go for a wiggle. And b is approximately 0.68. So all you're doing is comparing this equation here with y equals mx plus c. So instead of having y on your y-axis, you'd have log of y. And instead of having an x on your, well, no, sorry, and you've still got an x-axis here. So the only time that this wouldn't be the same is when you are trying to do something where you're going to get a log x in there. So how would that happen? So if instead of being in the form y equals a to the power bx, say it was of the form y equals a x to the power b. So this time we've got a power. So when you take logs of both sides, you'd get this. Split that second log up into log a plus log x to the power b. Bring your cheeky b forward. Whee! Oink. And that would give you log y equals log a plus b log x. So now when we compare this with y equals mx plus c, I'm just rearranging the order here because the x term's over here, but if you wanted to you could move that over there so it's in the right place for you. Anyway, either way, so this time you would be plotting, your x-axis would be log x, your y-axis would be log y. Okay, so you'd be plotting log y here, log x here. Okay, so you'd need to calculate, if it had a table, you'd need to calculate all your log y's and all your log x's for all your x and y values. Okay, then your y-intercept is log a still, but this time your gradient would be b. Okay, so on this one, when you plotted those, you get a straight line, something like that. This here, your y-intercept, that's your log a, and your gradient of this line is log b. Right, I hope that's helped you understand it a little bit more. If it hasn't, give me a shout and we can go through it again tomorrow. Okay, hope that helps. Toodle-oodle.